Hello students. So last class we have discussed about the introduction to atomic structure, and we have defined what do we mean by atom, and regarding its historical background also, different concepts regarding atom structure of atoms was given by different scientists. I have told you, and particularly we have discussed about the discovery of nucleus by Rutherford. And this model, you have to remember, atom consists of a central positive charge core that is known as a nucleus, and where neutron and protons are located inside the nucleus, and electrons are present in the extra nuclear portions. The electrons are revolving around the positive charge nucleus, just like the planets are revolving around the sun. That's why these are known as planetary electrons we have discussed. Okay, so we will go through the drawbacks of Rutherford model, little bit discussing something that is remaining over here. So subatomic particles also we have covered, electrons, protons, neutrons, and how to calculate all the things. And another one is I have forgotten to tell you, that is isoelectronic species. Okay, isoelectronic species. ठीक. So these are the species particularly having same number of electrons. Okay, the atoms, the species, whether these are neutral atoms or ions, having equal number of electrons, are called isoelectronic species. These are known as isoelectronic species. For example, very simple. For example, if I consider here O2 minus F minus. Okay, you see. So oxygen having how many electrons? Normal oxygen atom, how many electrons? That is 8. Again, this 2 minus, it gains 2 electrons. So 2, that will be 10 electrons. Like that of F minus. Normally the neutral fluorine atom having 9 number of electrons, plus it gains 1 electron, that is 10 electrons. Since both these species have equal number of electrons, that's why this O2 minus and F minus are isoelectronic to each other. Similarly, Al3 plus. Okay, in case of aluminum, its atomic number is 13. So number of electrons, that is 13, and due to 3 plus, it has lost 3 electrons. So you have to subtract 3 over here, that is 10 electrons. This one is also isoelectronic to this F minus and O2 minus. So the species having equal number of electrons are isoelectronic to each other. Okay, just remember this one. Next, we will discuss a numerical, that is, so here you see, calculate the number of protons, neutrons and electrons in bromine 3580. So you see, very easy, बच्चों जैसा खेल है, आपको ये 35 इसका एटॉमिक नंबर है और ये 80 इसका मास नंबर है. ठीक है, तो नंबर ऑफ, सबसे पहले नंबर ऑफ इलेक्ट्रॉन्स, टेल मी, इट्स इक्वल टू इट्स atomic number, because it is not a charged species. There is no minus and plus charge mentioned in this. This one is completely neutral species. So number of electrons equal to its atomic number, that is 35. And clearly number of protons also 35. Okay, then you calculate number of neutrons, that is A minus Z. So that will be 80 minus 35. So that can be your 45. That is your number of neutrons. Okay, easy. So we will go through next numerical, that is So here you see the question is the number of electrons, proton and neutrons in a species are equal to 18, 16 and 16. So you just first write down number of electrons that is 18. Okay. Number of protons that is 16. Number of neutrons that is also 16. Then identify the species. Okay, you know there only the variation of electron takes place depending upon whether the species gains electron, then it carries negative charge. If it loses electrons, then it carries positive charge. So species varies only on the basis of number of electrons, but number of neutrons and number of protons are fixed. So here the number of protons is 16. Clearly the atomic number of the species that should be 16. So clearly this 16 correspond to S. Okay, and number of neutrons, if you predict its mass number, it's normally 32, you know. If you predict its mass number that is equal to number of protons plus number of neutrons, that will be 16 plus 16, that will be 32. So 16, this is 32. Okay, and it is mentioned that number of electron is 18, that means it gains extra 2 electrons. So for this you can mention over 2 minus. So the species is sulfide ion, S2 minus. Okay, that is sulfide ion. Clear? Very good. So now we will discuss very important, that is wave nature of electromagnetic radiation or electromagnetic wave theory. Okay, wave nature of electromagnetic radiation, or you can say theory of electromagnetic waves or electromagnetic wave theory. Okay, so it means genuinely this theory was given by James Clerk Maxwell. Okay, so this theory was given by James Clerk Maxwell in 1864. According to him, energy emitted from any source you can imagine, normally light source or by means of any electric bulb you can say, or from sun, the energy that is coming from sun towards us also. Okay, or you may strongly hit an iron rod. Okay, so the energy that is emitted by such bodies, okay, these are the source of energy. Okay, where energy is emitted. Okay, so these such energy that is coming from such source are regarded as radiations. Okay, energy is emitted in the form of radiations. That's why these are known as radiant energy. And such emitted radiation, it occurs through continuously. Okay, continuous emission of energy. Okay, so following points you have to note it. Okay, this theory states that the energy emitted from any source, you can imagine electric bulb or red heated iron rod okay, continuously in the form of radiation, in the form of radiation. That's why such radiations are also known as, such energetic radiations are known as radiant energy, and is called radiant energy. Radiant energy. Okay. Next, such radiant energy, okay, such radiations, according to this theory, such radiations consists of electric field and magnetic field, which are perpendicular to each other and also perpendicular to the direction of propagation, to the direction of propagation of the radiation, okay. Again, they possess wave character and traveling with the velocity of light, that is 3 into 10 to the power 8 meter per second, okay, travels with the velocity of light. Due to the above nature, due to the above characteristics, okay, such radiations are known as electromagnetic radiations. Such radiations are called electromagnetic radiations. Okay, and the special characteristic is they do not require, okay, the special characteristics of such electromagnetic radiations, they do not require any material medium for their propagation. They do not need any material medium for their propagation. Okay, as you know, the energetic radiations which are emitted by the sun and it is coming towards us, there is no material medium, it proceeds through it coming through vacuum, no material medium is required. Okay, so these are the few important characteristics of here, that is electromagnetic radiations. Okay, so let us show how actually they propagates, how an electromagnetic wave, since it possesses wave character. Okay, so we have to discuss all the parameters of a wave. Generally we should discuss about that, but before that let us see how actually it propagates. Okay, So you see, suppose this one is your x axis and this one is your y axis and this one is your z axis. Okay, so electromagnetic radiation, one is it possesses wave nature, so this is wave nature. Okay, and this component that is parallel to z axis. Okay, and it is generally present your zx plane. Okay, this plane, zx plane. This is your electric field component. This one, is your electric field component. Okay, and another one that is, you see, this one. This one. Okay, so this is your magnetic field component. Magnetic field component. These two fields are perpendicular to each other. You see, suppose one is this one. Okay, so it's like this, and another one is this one in this plane, and another one is this plane. This is magnetic component. Okay, so these two are, suppose this one is your magnetic component lying this, and electric field component will be lying vertical to each, perpendicular to each other. Okay, so you see, this line, that is magnetic component, is present in your xy plane, that is lying parallel, this, like this is, okay, magnetic components like this, and electric component is just perpendicular to it. You see, this one is magnetic component and this one is electronic component. You see, okay, so this is, these two are perpendicular to each other, to the direction of their propagation. Okay, so since this is wave, so wave, you know the parameters of wave, it must associated with wavelength, velocity, frequency, okay, time period, all these things. Okay, let us discuss about the parameters of the wave natures of your electromagnetic radiation. So first one, if I represent a genuine wave like this, okay, so first one, that is wavelength. Wavelength is represented by lambda. Okay, so it is nothing but the distance between two consecutive crests. Okay, it is the distance between two consecutive crest or true. So these are crest and these are true. Okay, so lambda, it is the distance between any two consecutive crests, or you can say two consecutive truths. Okay, so it is, since it is a measure of a distance, so its unit you can say angstrom. 1 angstrom, that is 10 to the power minus 10 meter, or you can say 1 nanometer, that is 10 to the power minus 9 meter. Okay, 10 to the power minus 8 meter. Okay, so that is your 1 angstrom, that is, okay, so this is 10 to the power minus 8 centimeter, you can say, that will be 10 to the power minus 10 meter. Okay, 1 nanometer, 1 picometer, that will be 10 to the power minus 12 meter. So this is your wavelength. It is the distance between two consecutive crests or two consecutive true, you can say. Okay, or since these are the nodal regions, you may also consider this wavelength is the double of this nodal regions. Okay, here from here to here, this one also your wavelength. Okay, so you just remember for simplicity, it is the distance between consecutive crests or consecutive truths. Okay, so after this wavelength, another characteristic, that is your velocity. Okay, that is velocity. Velocity means distance covered per unit time. Okay, so it is the distance traveled by the wave in 1 second. Okay, the distance traveled in 1 second, that is your velocity. Okay, so velocity unit, that is centimeter per second, or you can say meter per second. Okay, since all electromagnetic radiations travel with the velocity of light, so its velocity is taken to be 3 into 10 to the power 8 meter per second. Okay, so next, after velocity you can compare, that is frequency, that is represented as nu. Okay, so frequency means it is the number of waves passed through a point in 1 second, that is called frequency. So frequency unit, that is cycle per second, or you can say simply second inverse. So frequency is the reciprocal of time period. Okay, so it is second inverse, you can say. Clear? Next, wave nature, wave characteristic, wave parameter, that is your frequency. Next is wave number. You can say wave number, that is represented as nu bar. Okay, it is the number of waves passed in 1 centimeter distance. Very simple, this wave number is nothing but reciprocal of your wavelength. Okay, so unit you tell me, that will be centimeter inverse or meter inverse. Clear? Now another parameter you can say, that is your time period. So time period, this is tau bar, it is represented by tau bar, time period. So time period, the time taken for one wave, the time taken for a wave to pass through a point. So simply it is the reciprocal of your frequency. Okay, so unit you can tell me, frequency is the reciprocal of a time period second inverse, so its unit simply second. Okay, second inverse, that will be second will be its a unit. Okay, that clear? Very good. So here you see the question is calculate the wave number and frequency of radiations having wavelength this much angstrom. Okay, so easy, you have to calculate wave number, that is this one, reciprocal of wavelength. So first you convert this wavelength lambda, that is into 5800 angstrom, convert it into SI unit, 5800 into 10 to the power meter. If you convert it into meter, that will be 10 to the power minus 10 m meter. Okay, so nu bar wave number, that is reciprocal of wavelength, so 1 by lambda 1 by 5800 into 10 to the power minus 10 m. Okay, so the value you just calculate it and it will be coming out to be 1.72 into 10 to the power 6 meter inverse. Okay, next you calculate its frequency of radiation. So you just remember very important formula, that is c is equal to nu lambda. Okay, you just remember it is the relationship between velocity, frequency, wavelength. Very important. Remember this formula, c is equal to nu lambda. Okay, c is equal to nu lambda. So by applying this formula you can calculate the frequency of radiation. Frequency is nu, so nu that is equal to c by lambda. C that is 3 into 10 to the power 10 meter second inverse divided by lambda, you have got 1.72 into 10 to the power 6 meter inverse. Okay, so the answer will be, just calculate this is frequency. Okay, so you will get the answer that will be coming out to be 5.172. 5. This one lambda, reciprocal of lambda, oh sorry, this one is meter. Okay, so this is meter, so meter get cancelled, so second inverse will be the unit of a frequency. Okay, so its answer will be 5.172 into 10 to the power 14 second inverse. Okay, so these are simply numericals. By considering these formulas you can solve it easily. Okay, very good. So next we will discuss very important another theory, that is called Planck's quantum theory. Planck's quantum theory of radiation, or you can say this one is the particle nature. After wave nature we have discussed detail of electromagnetic radiation. So now another nature also, that is particle nature of electromagnetic radiation. Okay, so the first point, that is the radiant energy observed or emitted not continuously. In that particular moment we have considered continuous absorption. Okay, so not continuously, rather discontinuously, in the form of small discrete packets of energy, called quanta. Okay, in case of quanta or quantum. Okay, and in case of light, it is each quanta is called a photon. Each quanta is called a photon. Okay, so continuously and discontinuous, very simple. This one is continuous. Okay, and discontinuously in the form of small packets like this. This is discontinuous energetic radiations or particle nature of energetic radiations. Okay, so each packet, each bundle is called quanta, or you can say quantum. If this is ordinary light radiation, then you can say photon. Okay, and the energy of each quanta Okay. Next point, this is discontinuous. Okay, the energy of each quanta, the energy of each quanta, the energy of each photon or quanta is directly proportional to frequency of radiation. Okay, so E is directly proportional to nu. E is directly proportional to nu. So if I remove this proportionality, then there should be a constant, since it is given by Planck's. So this H is known as Planck's constant. E, that is equal to H nu. Okay, this H is your Planck's constant. Planck's constant. This is the energy of each photon. Okay, Planck's constant, and its value is found to be 6.625 into 10 to the power minus 34 joule into second. This is the value of Planck's constants. Okay, so energy absorbed or emitted, okay, that is quantized. Quantized means you can write E, that is equal to NH nu. NH nu matlab this N is an integer. So energy absorbed, it can be 2h nu, 3h nu, 4h nu, 5h nu, likewise quantized. Okay, they are whole numbers, quantized. Clear? So now if E is equal to, next another little bit of derivation is there. If E is equal to h nu, E is equal to h nu, very important, we have to proceed several numericals based on this formula. Okay, just remember E is equal to h nu. Okay, so as we know, C is equal to nu lambda. Okay, then tell me what is the value of nu over here. Nu is equal to C by lambda. Now substitute this one over here, so you will get E, that is equal to h C upon lambda. It's a very important formula. Very important formula. E is equal to hc by nu. Okay, so from here you can clear that that energy increases, that means frequency also more. E is equal to h nu. E is direct proportional to nu. Matlab if more the frequency of radiation is there, more will be energy, and it is inversely proportional to wavelength. So if energy is maximum, then wavelength will be low. Low wavelength correspond to high energy, and high energy means high frequency. Okay, just remember this relation. Now we will do a few numericals on this formula. Okay, so let us discuss. So you see the numerical, calculate the frequency, that means you have to calculate nu. Okay, frequency and energy of photon of radiation. E is equal to how much, frequency is equal to how much, having wavelength 6000 angstrom. Very easy. So wavelength lambda is given you in angstrom, just convert it into meter, that will be 6000 into 10 to the power minus 10 meter. Okay, so you can calculate frequency that is equal to C by lambda. Just I have told you, very important formula. So velocity of light, that will be 3 into 10 to the power 8 meter per second divided by 6000 into 10 to the power minus 10 meter. Okay, so meter get cancelled, and you will get the value that will be found to be your 5 into 10 to the power 14 second inverse. 14 second inverse. This is the value of your nu frequency. Okay, and you can calculate easily. E is equal to h nu, value of h I have told you 6.625 into 10 to the power minus 34 joule into second, into frequency, that is 5 into 10 to the power minus 10 meter. Okay, so meter get cancelled, and you will get the value that will be found to be your 5 into 10 to the power 14 second inverse. Okay, so its value will be 3.31 3 into 3.3125 3.3125 into 10 to the power minus 19 joule. So this will be its answer. Okay, very good. Next we'll, so students, you see here, calculate the energy of 1 mole of photon of radiations whose frequency is given you this much Hz. Okay, so you just calculate the energy of one photon first. Okay, so the energy of one photon, that is equal to E, that is equal to h nu. So h will be 6.625 into 10 to the power minus 34 joule into second into 5 into 10 to the power 14 hertz. Okay, so energy of photon, that will be coming to be in the form of joules, in the unit of joules. Okay, so if you multiply this, so its value would coming out to be 3.313 into 10 to the power minus 19 joule. Then for 1 mole, I have told you 1 mole correspond to Avogadro number of photons. Okay, 1 mole of anything. So 1 mole of photon, for 1 mole of photon, that will be 6.022 10 to the power 23 into 3.313 into 10 to the power minus 19 joule. So its answer will be 19951 joule per mole. Okay, so now we have discussed your Planck's quantum theory of radiation and electromagnetic character. That means we have discussed that energetic radiations have two characteristics. The first one is wave nature, and according to Planck's, it also exhibit your particle nature also. Okay, and each the radiations are not continuous, rather they are discontinuous, and in the form of small packets of energy, and each packets of energy is called quanta or quantum. In case of light, you can say this is a photon, and energy of a photon, that is h nu. Okay, so clear? So till now I think you have got it very properly. So thank you for your kind attention. Okay, bye bye.